All right, picking up from where we left off in class last time, I want to look at sections 40.3 and 40.4 from our textbook. And so that's potential wells, and that's also potential barriers and tunneling. So that's what we're looking at. And you may recall from the last lecture, we had a classical analogy to a quantum problem. Here in the quantum problem, we have an electron that is incident on a potential energy barrier. We could imagine that potential energy barrier to be a conducting cylinder that's hollow. And as the electron moves toward the negative conducting cylinder, experiences repulsive forces which slow it down, so it has a slower velocity inside, but then it has enough energy to make it all the way through, so that the repulsive forces of the cylinder speed it back up again at the end. We could imagine that this is a sudden increase in potential rather than a gradual increase, just to simplify the problem. And so our classical analogy is what I wanted to show here, in which we've got a car that has a kinetic energy that is greater than the potential energy of this hill. And so if this car then moves in with a total energy that's greater than the potential energy of the hill, that means that by the time it gets to the top of the hill, even though it has less kinetic energy, it still has enough energy to make it up over the top. And then the hill, when it goes back down, will speed it back up again, and it will regain its original speed when it's on the other side. And so this is exactly what the electron will do if it makes it through this electric potential energy barrier and gets to the other side. We can call this region 1 here, this region 2 there, and this region 3 here. And so in region 1 then, we can write a solution to the Schrodinger equation that looks like A e to the I kx, we'll call this k1x, plus B e to the minus I k1x. Remember that e to the I k1x represents the motion of the electron to the right, whereas the B e to the minus I k1x would represent a reflected electron wave that bounces off of that barrier and moves with equal energy in the opposite direction. In region 2, this would be psi 1, and we would assume this solution in region 1. In region 2, we're going to have a different value for k because the wavelength will be different. Remember that p, which is equal to mass times velocity, is equal to h over lambda. And so if the velocity slows here, that means that we have a different wavelength, and therefore a different value for k, because we can also write this as h bar k, where k is 2 pi over lambda. Okay, and so the k1 then represents a lambda 1, but in region 2, a k2 will represent a different lambda 2. And so in region 2 then, we can write this as psi 2 is equal to c, different amplitude coefficient, times e to the I k2x plus d e to the minus I k2x. Okay. And so this then represents a traveling wave, one of which moves through to here, and this represents a reflected wave off of this boundary. You know, it may not seem like it should reflect off of a boundary if the energy is greater than the step height. But in any kind of wave phenomena, when the property of the medium changes, you have some percentage of the original wave will be reflected. And so this is different then from our classical analogy. In the classical analogy, if the energy is greater than the step height, the car makes it over the barrier 100% of the time. But that is not the case here because we have an incident wave and a reflected wave. And then that reflected wave can in turn bounce off of this surface, and you get an infinite series of reflections, which can be incorporated into the values of C and D. Okay, and so that is the solution to the Schrodinger equation in region 2. In region 3, we can write that psi 3, region 3, is equal to e to the I k3x. Okay, indicating that there is motion to the right of the electron, which makes it through this barrier, but there's nothing else to reflect it. So we don't have an f e to the minus ikx because there's nothing out here all the way to infinity to reflect the electron back. And so these are our solutions in each of the 3 regions. And so what we'll need to do then is to solve the Schrodinger equation in each of the 3 regions. So let me start out with the Schrodinger equation, minus h bar squared over 2m d squared psi dx squared plus u psi equals e psi. And for our purposes here, we could set E equal to, let's say, 4 electron volts, and U equal to 2 electron volts. Okay, so that E is greater than U, but we have specific values for them so that we can actually get a velocity for the electron under the influence of this electric potential. So what we'll do then in region 1 is plug in to the expression for the Schrodinger equation the solution for the Schrodinger equation in region 1. Okay, so this is minus h bar squared over 2m times the second derivative of psi in region 1 with respect to x squared. And so d squared psi 1 dx squared is equal to minus k1 squared times psi 1 back again. Okay, and so we can get that by just plugging in these values for psi 1, taking 2 derivatives. And so what that'll end up doing then is giving us a factor of minus k1 squared multiplied by psi back. Okay, and so that's what will go in here. Minus k1 squared psi 1. And so that's our second derivative of psi with respect to x squared. Well, let's just quickly go through how that would work. Here, if we have the derivative of psi 1 with respect to x, total derivative, that would be minus k1 a e to the I k1x, that would be plus k1 times e to the I kx. So that would be this first term, if we differentiate that. The second term, if we differentiate that, that would be equal to minus I k1b e to the minus I k1x. And then if we take the second derivative of this, d squared psi 1 dx squared would be, you'd have an ik again, so it would be I squared is negative 1, or minus k1 squared a e to the I k1x. And then here we would have, this is plus, and this is minus I k1. Okay, and so when we have another minus I times this minus, we get minus I k1 times minus I k1 times b e to the minus I k1x, or minus k1 squared a e to the I k1x. And here we have minus times minus is plus, I times I is minus 1, so it's minus k1 squared v e to the minus I k1x. Or that's just minus k1 squared times psi, where psi is a e to the I kx plus b e to the minus I k1x. Okay, and so that's the justification for this. And this is something that I would expect you to show on an exam. And we'll have to figure out how we're going to do exams, but this is the kind of detail that I'm looking for, which is the actual solution to the Schrodinger equation. So you'd want to go through these steps and make sure that you can do it. Okay, and so that's this part. And so basically then that's just gotten by assuming that this is the correct solution. And then we're going to find the value for K1 that satisfies that solution. And so here we'll have plus U psi equals E psi. Okay, so the psi's are going to cancel out all the way through. And so what we get then is just h bar squared K1 squared over 2m equals E minus U and that's it, because the sides have canceled. And then if we solve this, so basically what we're doing here is we're finding a condition on K1 that satisfies the Schrodinger equation with this assumed initial solution to the Schrodinger equation. So this gives us K1 is equal to the square root of 2m times E minus U divided by the square root of h bar squared is just h bar. Okay. And so this then is a connecting link between K1, the mass of the electron, the energy total of the electron, which we said here was 4 eV, the potential energy, which we said was 2 eV, and so this can all be crunched down to a number. And so that'll be our value then for K1. What about the potential energy in this region? What would it be? What do you say when you don't know the answer?
0.
0, that's right. And so this is the solution then in region 1, because the potential energy function is 0. So that looks like that in region 1. Whereas in region 2, you can make the same initial assumption for the basic form of the Schrodinger equation, but with different amplitude coefficients, C and D. Why are they different? Because some of the electron probability has reflected off of this surface. And so that means that there is less left to move through this region because some is reflected before it's ever gotten to this region. And so that means that these amplitude coefficients can't be the same as the A and B coefficients of the electron before it got to that potential energy barrier. And so we can do the exact same thing here with psi 2 and put in here K2, and we can work this all the way through, but just with a K2 instead of a K1. If you're doing this in your notes, you might want to actually rewrite the expression. K2, K2, K2. It's all the same, except that we've switched now, and we're now in region 2. This is K2, this is K2, this is K2, this is K2, and this is K2 squared times psi 2. Okay, so we can do the exact same thing in region 2, and so this gives us K2 equals square root of 2m times E minus U over h bar. So it's similar to the expression in region 1, but in region 2, we've got a potential energy function that's not equal to 0. Okay, and so this basically is telling us then that the total available kinetic energy is less, and it's less by an amount that's equal to E minus U versus here, what it was when it was just E. Okay, and so this is going to equal 2 pi over lambda 1 for K1, and K2 is going to be 2 pi over lambda 2. Okay, so this means now that we have expressions for the wavelength of the electron in region 1 versus the wavelength in region 2. And I think that it should be clear from this that the wavelength in region 1 should be less because K1 is bigger. K1 goes like 1 over the wavelength, and it's bigger by an amount E versus E minus U. And so with a bigger value for K, that means we have a smaller value for the wavelength. Whereas a smaller value here for K, E minus U instead of E in the square root, is going to give rise to a larger wavelength. So the wavelength will come in like this. This wavelength here we could call lambda 1. And then that wavelength is going to stretch out a little bit to lambda 2. Now what about in region 3? Well, in region 3 it's going to go back to the same wavelength that it was in region 1. So this is lambda 3, and lambda 3 equals lambda 1. How do we know that? Well, in region 3 we have the exact same solution that we had in region 1, which looked like this. Okay, so that it's just for the e to the I k3x. We take two derivatives of that. We get minus k3 squared times psi. And we plug that into the Schrodinger equation with the u equaling 0. And we get this value for k3 as well. And so that means that lambda 1 equals lambda 3. So we don't have to necessarily spend 20 minutes of algebra going all the way through the Schrodinger equation to just solve the same equation again in region 3, because we see we have identical conditions in region 3 that we had in region 1, which is just kinetic energy and no potential energy. And so therefore, in this, both regions 1 and 3, the K1 value can be calculated. Let's go ahead and do that. K1 would equal the square root of 2 times the mass of the electron, so that's 9.1 times 10 to the minus 31 kilograms, times the energy, which is 4 eV. Don't forget to convert that into joules inside of the square root. That's 1.6 times 10 to the minus 19 joules per eV. And that's all divided by h bar. So h bar we can rewrite as Planck's constant over 2 pi, 6.63 times 10 to the minus 34 joule seconds. So this then is our value for K1. So we just have to knock this out on the calculator. And so that gives us 1.02 times 10 to the 10th power. And so that would be in units of 1 over meter. And so is that a reasonable number? Well, if we want a wavelength that's on the order of maybe an atomic diameter, let's say here that L is 1 angstrom, then we can rewrite this then as 2 pi over lambda 1. So lambda 1 would be equal to 2 pi divided by 1.02 times 10 to the 10th power. And so that gives us 6.14 times 10 to the minus 10 meters. So that's lambda 1. But once you've got lambda 1, you've got lambda 3 as well. Because we know that the wavelength in this region, although the amplitude is not as high, the wavelength is the same. Now what does this mean? What this means is if the electron makes it through the barrier, it's traveling just as fast as it was over here. But it doesn't mean that it's got more energy. It just means that it has more probability. If it's on this side with a higher value for the amplitude, that tells us that over here, it won't be found as often when you make the measurement. But when you do make the measurement and you find it over on this side, it has just the exact same speed that it had on the other side. And so the amplitude is not influencing the total energy or speed of the particle, but rather is influencing the likelihood that in a given measurement you would find it in this region versus in that region. Okay, so let's go one more step with this and find the velocity of the electron in regions 1 and 3. So the velocity 1 will equal velocity 3, and that'll be equal to h over lambda 1. And that's also equal to h over lambda 3, because lambda 1 equals lambda 3. Okay. And so that velocity, that's the momentum in these regions, mv1 and mv3, h over lambda 1, h over lambda 3. So that means that v1 is equal to h over m v1. Okay, so that's what I meant to do. And m, of course, is the mass of the electron. Okay, and so, but v1 will equal v3. So once I've done it for v1, because k3 is equal to k1, then v3 is equal to v1 as well, because it's just inversely proportional to the wavelength. So v1 then is going to be 6.63 times 10 to the minus 34 joule seconds for Planck's constant divided by the mass of the electron, 9.1 times 10 to the minus 31 kilograms, times, this should be lambda 1, there. Okay, and so lambda 1 we have over there is 6.14 times 10 to the minus 10 meters, or remember that's 6.14 angstroms. So that is a wavelength then that's about 4 times the length of this barrier in the conditions that we're looking at here. So let's knock that number out, and that'll tell us how fast the electron is moving in regions 1 and 3. So that gives us 1.18 times 10 to the 6 meters per second. So that is roughly 1.5 times 10 to the 6 would be about 3 times 10 to the 6 would be 1/10 the speed of light. And so this would be maybe between 1/20th and 1/30th the speed of light. Okay, so it's still a classical problem, and v1 is equal to v3. So this would also be the velocity of particle 3 if it makes it through that barrier all the way to the other side. Okay, what about in region 2? Well, in region 2, we have a value for k2 that looks very similar. Notice here that k1 is the square root of 2me over h bar, and k2 is the square root of 2m times e minus u over h bar. Okay, so it's going to be a similar kind of a calculation for k2, but with a slightly smaller value. So k2 will equal square root of 2 times the mass of an electron times e minus u, so that's going to be 4ev minus 2ev, then multiplied by 1.6 times 10 to the minus 19 joules per ev to cancel out the ev units. And then that's all going to be divided by h bar, which is Planck's constant, divided by 2 pi. So again, we can write this as 6.63 times 10 to the minus 34 joule seconds times 2 pi. And that'll be K2. Okay, now, we can see from here that K2 is related to K1 by a factor of 2 inside of the square root sign. Because here it's just 2, the square root of 2. Here it's the square root of 4. Okay, so the difference between them is the square root of 2, right? Because it's a 2 inside of here. If you multiply this by a 2 in here, then that equals that. Okay? And so if you take this, K1, and divide by the square root of 2, you'll have K2. Now if you don't believe that, just multiply the whole thing out. But K2 is a little less. It's equal to 1 over the square root of 2 times K1. So that saves me a little bit of time in this marathon calculation session. But go ahead and just work the thing out yourself, and you'll get that result if that explanation for the relationship between K1 and K2 is confusing to you. So this will then just give us, well, we had K over here. That was 1.02 times 10 to the 10. Then we just divide that by the square root of 2. And that gives us 7.21 times 10 to the 9. That would have units of 1 over meter. Okay? And so then that K value can be related to lambda 2. So lambda 2 then is going to equal 2 pi over K2. And so that'll be equal to essentially 2 pi divided by 1 over the square root of 2 times K1, because that's what K2 is equal to, 1 over the square root of 2 times K1. So that's the square root of 2 times lambda 1, which I'm again doing instead of working through all the calculations. I'm just comparing them, seeing that they differ by a factor of the square root of 2. I know that lambda 2 is bigger, so it must be bigger than lambda 1 by a factor of the square root of 2. So lambda 1 was 6.14 times 10 to the minus 10. Multiply that by the square root of 2, and I've got 8.68 times 10 to the minus 10. So that's meters, or 8.68 angstroms. And then finally, V2 is going to be a little slower by the factor of the square root of 2 from V1. And so V2 is equal to V1 over root 2, because they're all differing by a factor of the square root of 2. We know that V2 is smaller than V1 and V3. And since V1 here was equal to 1.18 times 10 to the 6, and we know that it's going to be smaller than V1 by this factor of the square root of 2. So that gives us 8.34 times 10 to the 5. Meters per second. So this is how we get a physically measurable quantity out of all of the math that's involved with the solution to the Schrodinger wave equation, where we've applied the different values for psi that are assumed solutions for psi in regions 1, 2, and 3 separately into the Schrodinger equation, found the condition on the k's, and then related those k's to the wavelengths and velocities of the electrons in each of the different regions. Okay, so that takes care of the solution in what we could call case 1 here, where the energy is greater than the step height. But there's one other thing that I wanted to talk about, and that's the probability of it making it through the barrier versus the probability of it being reflected by the barrier.